All right. So what's the logistic growth model basically? Now, when you look at the logistic growth model, generally what happens is that the first thing that comes to your mind is actually what's the nature of the growth. So when you look at initially the growth of any logistic curve is actually the S kind of shape that you get. So what happened is that, let's say this is starting from almost, let's say 0. Initially the growth is following exponential trend, and then what happened is that it reduces in its nature and it becomes stagnant almost. So the rate of increase decreases actually. So what promotes the exponential nature? So this is the specific backbone for differential equation that is for logistic growth. So if the rate of change of that, let's say this is P is the population and T is the time, and if the rate of change of population is proportional to, so if dp by dt is initially proportional to p, because this is what is the exponential model. And when dp by dt is also proportional to 1 minus p over a, or here this factor is basically that is what limits the growth. So when the function, or let's say the population value approaches to a, that is stagnant a value here, uh, you can see that the curve doesn't go beyond that. So let's just take an example of the population growth using the logistic model. Here's an example. So let's say the population of an island is currently 154. Its expected growth rate is that dp by dt is 0.16 p, 1 minus p over 500, where t is the time in years of this differential equation. So to solve, you first thing you're going to isolate them, like how we did the separation of variable. Then this is something you can see that there involves two factors in denominator. So you express this as a partial fraction, where I have shown it here. So 1 over p can be written as a over p plus b over 500 minus p. Now, if you cross multiply it here, you get this relation, which is here. And once you substitute p as 0, you get a is 1 over 500. And once you substitute p as 500, so you get b as 1 over 500. So this basically can be written as the value of a and b both is 1 over 500. So what we can do is we can actually calculate the expression value easily. So what we can do is, if you substitute back the value of a and b in this, this expression, this 500, which was earlier, it get canceled, and you eventually get the expression that you can integrate, which is 1 over p plus 1 over 500 minus p. So now we are reaching this step here. Now you integrate both the sides. So this integration is ln p, this integration is ln 500 minus p over divided by coefficient of p, which is -1. This integration is 0.16 t. And if you apply ln a minus ln b, it can be written as ln a over b equals to 0.16 t plus c. So if you get rid of ln, it is p over 500 minus p is plus minus e to the power 0.16 t plus c. So if you reciprocate it, obviously what happened is that this becomes, I can rewrite this as plus minus e to the power 0.16 t into e raised to c. So if you reciprocate this, this become e to the power -0.16 t, and they have taken this as another constant, b. And once you make p the subject, so 500 minus p over p, if I make the subject b e to the power -1/t here, I get the exact logistic model. So let's see what exactly it is. So I get the logistic model, which is here. That is this step. So this is a general logistic curve that we got. And now you can just substitute the values of t in order to get the exact value of p. So the critical steps are expressing a partial fraction, expressing a particular like logistic model as a partial fraction, which I did here, and then integration and a little bit of the simplification step. So now, as you can see that when my time becomes infinity, this part becomes 0. So that's why this population becomes stagnant as 500. So this is an evidence of your understanding. And so sometimes when they say find the limiting population, that is what it means, that, okay, what's the maximum value of the population that it can reach to. So this is how you do the logistic model and the application of logistic model. All right, so here's the another example on the logistic curve. So the first one is dp by dt of is given by 0.2 p times 1 minus p over 200. Initial population has been given as when t is 0, p is 220. Write down expression for p as a function of time. So basically, got to solve the differential equation. Now what I do is I take LCM, firstly, of the right-hand side, and transform it to the left-hand side, isolate the variables. Now our need is to integrate this and this. The right-hand side can be integrated easily, but this one, you got to express this as a partial fraction. So I'm just first I'm just gonna express 200 over p times 200 minus p as a partial fraction, which is a over p plus b over 200 minus p. Now you solve for p, which is gonna give you a is 1 and b is 1. Now, once you got the value of a is 1 and b is 1, I'm just going to substitute this expression rather than this one. So this I won't use now. I'm going to use this expression. So what do we get eventually is the next step of integration, that is this one. So when you're integrating now this part, if this integration is ln absolute value of p, this is ln absolute value of 200 minus p over -1. So now this is ln a minus ln b. Since you know ln a minus ln b is ln a over b, what we get is this step equals to 0.2 t plus c. Now if you get rid of this ln, it becomes e to the power 0.2 t plus c. Now if you get rid of this absolute value, you get plus minus here. Now if you reciprocate this, actually what you get is, if I reciprocate this, I get e to the power -0.2 t and e to the power -c. And if I consider this as my new constant, this is a new constant a that I took, and then you cross multiply and make p the subject. If you bring the terms one side, like I can bring p here and I can take p common. So what you get is this expression. Now, what is really interesting about this expression is that if you now put the values, like initial value, if I take t as 0, I get population as 20. So you get a as also, like if you take, let's say, limiting population, if you want to find out. So limiting population is that when t tends to infinity, your expression is e to the power -0.2 t will tend to 0. And hence the population is 200 over 1. So that's something which is 200 is the limiting population. And if you wanted to do the initial population they had given was 20. So that gives you the a value. So a value comes to be